In this class, we are going to summarize what we have learned in the previous classes. We have analyzed two circuits or two networks by applying KVL and KCL. Okay, and we have find out the branch currents and other parameters also. And in this class we will summarize it, and you will, at the end of this class, you will get a procedure, step-by-step procedure to analyze to analyze a circuit or a network using a using mesh analysis, and also loop current analysis, you can call it. So we will start. And also we will be in a position to discuss the matrix method of solving or analyzing a circuit. Why we go for a matrix format? Why we go for a matrix format is that, suppose we have some circuit like this, having some having a large number of elements interconnected. So in this case, if you are going for mesh analysis or nodal analysis, we have a large number of nodes or meshes associated with this. Okay, then in that case, solving, we will get 1 2 3 4 5, if it is okay, in this case 5, and if we have a large number of networks connected like this, then you will get 5 6 7 8. That means I1 I2 I3 I4 I5, etc. I10 or I11 you will get. So you will get 11 equations. So you have to solve 11 equations. So that is bit of tedious or difficult job. So what we will overcome this by introducing matrix. Okay, and matrix, and we will get a matrix like this: I1 I2 etc. I11, and we will solve for this I1 I2 I11 by taking the inverse of coefficient matrix. This is coefficient matrix. So inverse of this coefficient matrix, that we will discuss later. Now, first of all, the loop analysis or mesh analysis, we have already discussed. We have already given an example, and you have also solved some problems, but in this class I am going to systematically how you can solve it. Okay, you have to follow all these steps in order to carry out a mesh analysis or a loop current analysis. Okay, so that yes, for any problem you have to follow this procedure or these steps. Okay, now we shall present this method by analyzing a circuit give an example circuit like this. Here I have another cell like this. So this is 9-volt battery. This is 4 ohm. This is 3 ohm. And then this is 1 ohm. This is 2 ohm. This battery voltage is volt. This is a 7-volt battery. Now, step 1 is to recognize the independent loops. To recognize independent loops and label the loop currents. First step is to recognize the independent loops and label the loop currents. Yes. How to recognize the independent loops? First of all, how many loops are here? Let us examine. This is one loop, and this is means like this, and this is another loop. This is another loop, and another loop is like this, the outer loop. Now, what do you mean by independent loop? Independent loop means the loops which are not carrying any loops within that loop. Because here this loop is L1. I'm naming this loop as L2, and this is L3. So L3 is not an independent loop because L3 is having two loops within the L3. So it is not an independent loop. Now, yes, let us mark. Let us mark the. So we have identified the. So the first step is to identify independent loops. So we have identified the independent loops as L1 and L2, and then we will mark two loop currents I1 and I2. So these steps are true, or these steps you can apply to any number of loops and any type of circuit. Okay, that is the beauty of this procedure. So now step 2 is write KVL equation. Write KVL equations for each loop. For each loop in the special form. Yes, in the special form that sigma voltage drop across each resistor and also across the components like battery and all other elements is equal to 0. So you have to, and you should follow our convention, and that we are going in clockwise direction. All those such conventions you have to follow. That means falling potential means negative, rising potential means positive. So you have to follow that. So you know that. So I will not explain that. So that is the what our step 2. Now step 3 is step 3. Step 3 is solve for the loop currents and compute currents or voltage required. Yes, we will get, in this case we will get two equations in two unknowns. So you solve those two equations using calculator. Okay, using calculator, or you can say, you can also in matrix format also you can solve it. I will yes, I will explain now. So okay, so the first loop equation will be 7 minus 1 into I1 minus 2 into I2 into 2 into S2 into I1 current is flowing, and also I2 current is also flowing. So I1 minus I2, I1 minus I2, and then we have a voltage drop, falling potential minus. Okay, yes, this is equal to 0. So 7 minus I1, so 7 minus I1, 7 minus I1 minus 2 2I1 2I1 minus 2I1 plus 2I2 2I2 minus 1 is 0, and we will get 7 minus 6 1. So 1 equal to I1 plus 2I1 plus 2I2, and that's equal to 3I1 plus 2I2 equal to what? Equation number 1. This is equation number 1. And similarly we have the other loop equation. The loop equation as yes, here plus 6, then I will get I am going in clockwise direction. Clockwise direction means I have to here represent, I have to represent this here plus and minus. That means falling potential again. And here plus and minus, falling potential, plus and minus, falling potential. Here plus battery voltage, and here minus. So I will get as 6 and minus 2 ohm across 2 ohm resistance. We have I1 and I2 flowing. I am going in I2 direction, so I'm taking I2 as the reference. So I2 minus I1 going in the upward direction into 2, right? Now minus 3 I2 minus 4 I2 minus 9 equal to 0. So what you will get is 6 uh, 6 6 uh, 6 plus 2I1 6 plus 2I1 plus 2I1. Now I'm clubbing this I2 terms, that means here minus 2I2 minus 3I2 minus 5I2 minus 9I2 minus 9I2 minus 9I2 minus 9I2 I1 I2, that minus 9 minus 9 equal to 0. That means 6 minus 9 is minus 3, and 3 2i1 minus 9i2 equal to 3 you will get. So these are the our loop equations mesh by analyzing mesh. Now I'm going to write it in a matrix format. That means matrix, this equation 1 and equation 2 is equal to, in matrix format it is will be equal to some matrix into I1 and I2 equal to some constants. So this matrix this is known as the matrix of coefficients. Matrix of coefficients, and this is matrix of unknown variables, and this is matrix of constants. Matrix of constants. So the coefficient matrix will be like this. The first equation I'm considering, first equation, it is first row, and the coefficient of I1 and I2, 3 and 2. So 3, 2, here it is I1, I2, 3, 2, then next equation, next row, that is second equation, second row, then coefficient of I1 and I2, 2 and minus 9, 2, sorry, 2 and minus 9. Then our unknown variables, that is I1 and I2, equal to matrix of constants. Constants means the equal to term, that is the RHS term. That means 1 and 3. 1 and 3. 1, 3. So you have to solve this I1, I2 matrix. Okay, solve for I1, I1, I2. So I1, I2 equal to, you will get 3, 2, 2 minus 9 inverse into 1, 3. Right. So you have to find out the inverse of this matrix. That means inverse of a matrix you have studied in your +2 class. So that means adj A by determinant A. Okay, A inverse. So you find out this, and into 1 and 3 you will get I1, I2. So that is what the matrix method. Okay, or otherwise you can easily put this you can find out this inverse in your scientific calculator very. This just a matter of practicing it. So you take this inverse, okay, in your examination hall. You just first of all you press on mode button, and you will get a matrix option you will get, and then input A equal to this matrix and take its inverse into another matrix B. You input 1, 3, and you just multiply A into B, then you will get the answer. So that's all about this. Then yes, so you can either solve it by matrix method, or you can just solve it by solving 1 and 2. So matrix method is useful when a large number of variables is there. a large number of mesh currents are there, not just I1 and I2. Maybe having networks, some networks having I1, I2, I3, I4 and I5 or up to I4. Then you can go for the matrix method, or if you are having three or four mesh currents, then you can go for the matrix method. Now, yes, yes. The loop current method is useful when we wish to determine only one current or voltage. In such a case, we can define all the unknown loop currents to avoid path path except one loop current. The resulting equation can be solved for that one loop current. That means the uh, yes. For example, okay, that's the application. Now we will, yes, this is the uh, general steps you have to follow while solving the loop currents mesh analysis. Okay, now, okay, now I'm going to give you an interesting example problem. A network or a circuit like this. If I want resistance, then I have a current source, 2 ampere current source. I have minus 10 volt plus minus 10 volt. A ohm, 2 ampere. Yes, and this symbol represents an ideal current source, an independent ideal current source. So how will you proceed with the mesh analysis in this kind of a circuit where you will find ideal independent current source, or in general current sources in your mesh? So how will you proceed? Yes, no problem. Here, the first step always it is to identify the independent loops. So here we have two independent loops like this, and we are naming or giving two loop currents for this, I1 and I2. Okay, now let us uh, go to the next step, that is write KVL equations. So while writing KVL equations, you will get a doubt what to do with this current source, how to tackle this current source. Now I'm going like this, yes, 10 volt, right? 10 volt. First of all, I have to, yes, this ideal current source is having Sorry. Yes, here this is a problem. Now this ideal current source, sorry, this ideal current source, independent current source, is having its resistance infinity, like open circuit. Open circuit. That means an ideal voltage source resistance of an ideal voltage source is 0, right? And the resistance of an ideal current source is infinity. That means this circuit 1, I can redraw like this with resistance only 5 ohm. Okay, and this ideal independent current source is having a resistance infinity. Infinite resistance means it should be an open circuit. Then voltage source, it is in battery voltage, that means ideal voltage source, and it is having 0 resistance, 0 ohm means it is short circuit, like right. Now I have an 8 ohm, 8 ohm. This is 0 ohm, and this is infinite ohm, and this is 5 ohm. So this is my equivalent circuit of this circuit 1. Okay, and these two circuits are equal or equivalent, you can say. Now while applying KVL means we are writing the voltage drop equations around a closed loop, right? Now in this case we have identified that this I1 loop and I2 loop are actually not loops. Actually it is not closed path. So if it is not a closed path, it is not a loop, right? So you can say that. Why? Because if you write the equivalent circuit of the circuit 1, you will get only one closed path, like this, only one closed path, right? Yes. So, the truth or the fact is that this circuit 1 is having only one closed path or one loop, actually. So that we can apply, we will be able to apply KVL. So what we will do, we will consider this loop like this, okay, and we will apply KVL for that loop. So if you apply KVL for that loop, then what happens is, yes, minus to plus, clockwise direction, okay, clockwise direction, minus to plus, it is plus, that means minus to plus means a rise in potential, that means plus. So plus 10 volt, 10 minus this, yes, clockwise direction I am taking. So here plus, here minus. So this is the falling potential, that means negative. So and the current through this 5 ohm resistance is denoted as I1, right? So I will get minus I1 into 5, and this again going in clockwise direction. So again plus minus, current flows always from higher potential to lower potential, and it is a falling potential, so negative. So minus 8 into current, current through the 8 ohm resistance. That means that is nothing but I2. So minus 8 into I2. And we have again going in clockwise direction, so that I have not find out any voltage drop further. So I'm equating it equal to 0. So my equation is like like this: 5i1 plus 8i2 equal to 10. This is now our first equation. So in order to solve for I1 and I2, I1 equal to I2 equal to, we should have two equations. If we have two equations in two unknowns, then it is well and good. So we can solve for I1 and I2. But we only got one equation by applying KVL. Right now, but we are going. We also have another equation, second equation. If you closely observe like this, that means here the I1 current is flowing in the downward direction. I2 current is flowing in the upward direction across the element, that is the current source, ideally independent current source. So actually what we will get is this 2 ampere current is always 2 ampere current, right? So what happens is, yes, I'm going to consider a node N1 here. So what happens is the I1 current is flowing into this node and I2 current is flowing out of this node, while the 2 ampere current is flowing into this node, right? So in a mesh analysis, it is not like that. We have a in-node case here. That means mesh analysis is not equal to applying KVL always. Okay, in mesh analysis, we will apply both KVL as well as KCL. So here, the best example is this example. In this example, we are applying. We have came across with a problem that is what our ideal independent current source in a branch, right? So in order to overcome that problem, we are going to apply the KCL here. So if you apply KCL, what you will get is I1 plus, that means algebraic sum of currents entering the node equal to algebraic sum of currents leaving the node. That means I1 plus 2 equal to I2. That means I1 minus I2 equal to 2. So this is equation number 2. That means our I1 minus I2 equal to 2 is our second equation. So we have two equations in two unknowns. So solve for I1 and I2. So we will get I1 equal to I2 equal to some ampere. Right. So this is the approach that you have to take whenever a current ideal independent current source independent or dependent current sources is present, or if you come across this current source, okay, during while applying KVL. So this is what What do you mean by tackling with uh, independent current source? Now we are moving on to our next topic, which is very important topic as far as your university exam is concerned. So the topic is star to delta and delta to star transformation. Okay, star to delta and delta to star transformations are defined for any type of elements which are connected in star or either star or in delta. But for you, particularly for first years, only we are considering the resistive networks only. Okay, that means network or networks uh, consisting of resistances as components, electrical components. Okay, so suppose we have a delta network, that is closed network like this. Like this, we are having a network. Okay, and this is, let us say that uh, this is R1, this is R2, and this is R3. Okay, now its equivalent star network is like this. Let us say that is like this. Okay, this is a B, and this is C, and here also there is a B and C. So this is RA and this is RB and RC. Okay, now this delta network, suppose in your examination the examiner has given the values of R1 equal to, okay, some R1 ohm, R2 equal to some R2 ohm, R3 equal to some R3 ohm. The examiner has given these values which is connected in delta configuration. Okay, and the examiner is asking you to find out the equivalent star network. That means this network in which Ra equal to dash ohm, Rb equal to dash ohm, Rc equal to dash ohm. So you have to find out Ra, Rb and Rc. Now I am going to give the formula. The proof is not required for you. So you just by heart this formula. That means Ra equal to product divided by total or sum. That means RA equal to, yes, you, yes, this is A means this is A, right? This this terminal is B means terminal is, and this terminal C means this C is also C. Now I'm considering imagining this equivalent star network inside this. So okay, let's see. Like this. So this is RA, this is RB, this is RC. So RA will be equal to product divided by sum. Sum means all the resistors in the closed path or covering the RA. That means total sum means R1 is R1 ohm, so R1 plus R2 plus R3. So this is what I mean by total. The product means this RA branch is connected. RA branch is connected at point A. Okay, at point A, in which there are two resistances connected. Two resistances in the delta network is connected. So the product means this the resistances corresponding to the common point A. That means R1 and R3 are connected to point A. So product means R1 into R3. So RA will be equal to R1 R3 divided by R1 plus R2 plus R3. Similarly, RB equal to product means the resistances in delta network which is connected to point B or to RB. That means R1 and R2. So you multiply R1 and R2 and divide that by total sum. That means R1 plus R2 plus R3. So this total sum R1 plus R2 plus R3 is common for all the formula. Yes. And again RC will be equal to, RC is connected to point C, and point C is, at point C we have R2 and R3 of delta. So you multiply R2 and R3, R2 R3 divided by total sum, that is R1 plus R2 plus R3. Okay. Okay. This is equation 1, 2, 3. So this is our delta to star transformation. Now delta to star transformation. Now we have star to delta transformation. That means the in your examination the examiner has given star network like this, star network. Okay, this is A, B, C. This is star network. This is RA. The examiner given this RA is RA ohm, RB ohm, and RC ohm. Okay. So the examiner is given this. So you have to find out. You should find out the equivalent delta configuration of this equivalent delta configuration of this. That means this is A, this is B, and this is C. That means this is RAB, and this is RBC, and this is RC. Okay, that means like this. So the white color represents the in star network which is given by the exam. But you have to find out the blue network which is the delta equivalent of star. Okay, and this is RAB, this is RBC, and this is R. So the formula is RAB equal to RAB. We have two terminals A and B. RAB is connected between two terminals A and B, and this A and B two terminals, in these two terminals we have RA and RB of star network. So you sum RA plus RB, you add RA and RB, okay, and another term you will get RA plus RB plus, and then you multiply this RA and RB divide by the other the other resistance, that is RC. Okay, that means RAB is this. Then similarly RBC will be RBC equal to RBC. We have connected, it is present between B and C terminals. B and C terminals got connected the RB and RC of Y. So you sum RB and RC, and again another term you have to add, plus, that means plus RB and RC again multiplied by divided by the far resistance, that means the RA, that means the resistance which is not connected to the terminals of RBC, that is RA. Okay, so this is a term, this is one term, this is another term, so three terms you add up. Okay, similarly RBC is okay, then RCA will be equal to RCA is present between A and C. To A, RA is connected, to C, RC is connected, so RA plus RC plus RA into RC divided by the other far resistance, that is RB. These are the formulas. Okay, formulas for the technique for star to delta transformation.